So this is Linear Algebra Lecture 16, and the very last section of the chapter on matrices is an introduction to linear transformations. So we're familiar with the vector spaces Rn. So this is all n tuples of coordinates, all column vectors with dimension n, and Rm, which is the set of all column vectors with m coordinates, dimension m. And what is called a linear transformation T from Rn to Rm is a function T from Rn to Rm, which has the following two properties, such that T of x plus x, let me write it like this, T of x plus x prime is T of x plus T of x prime for all vectors x, x prime in Rn, and T of c times x is c times T of x for all vectors x in Rn and all scalars R. Right? So a linear transformation is a function that satisfies these two properties. And what's very important is that every m by n matrix A11 to A1n, AM1 up to AMN, defines a linear transformation T sub A from Rn to Rm. As follows. T sub A applied to a vector x is the matrix A applied to the vector x, written as a column vector, x1 up to xn. So this is a matrix times a vector. And you get the result is some m-dimensional vector. So this is the simple formula taken right from the book that associates to every matrix a linear transformation. And just as a simple example, suppose A is the matrix 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix. And this defines a function T sub A from R3 to R2. How is that? If you take x to be x1, x2, x3, any vector in R3, AX is the matrix times the vector. And you know matrix multiplication very well by now. This is x1 plus 2x2 plus 3x3, 4x1 plus 5x2 plus 6x3. And this is a two-dimensional vector. This is in R2. Right? This is my vector y in R2. And from the properties of matrix multiplication, distributivity says that A times x plus y is AX plus AY, because matrix multiplication is distributive. And A times CX is C times AX. So the properties of a linear transformation are satisfied, this additivity and this scalar multiplication property. So we have a linear transformation for every matrix. And there are various subspaces of Rn and Rm associated to a matrix or associated to a linear transformation. So let me draw a picture to indicate what's going on. Here we have Rn, here we have Rm, and we have this matrix A, which induces a linear transformation from this space to this space. So what is called the kernel of the linear transformation T sub A, it's all vectors x in Rn that get mapped to 0. So over here is the 0 vector, and anything that gets mapped to 0, that's the kernel of the linear transformation. And one vector that is always in the kernel is the 0 vector. So that's sort of a claim. The 0 vector in Rn is in the kernel of T sub A. And the proof is as follows. Zero plus 0 equals 0. These are the 0 vectors. So T sub A of 0 is T sub A of 0 plus 0. And by additivity, this is TA of 0 plus TA of 0. So I have this equation. And I don't know what TA of 0 is yet, but it's a vector, so it has an additive inverse. So TA of 0 minus TA of 0 is TA of 0 plus TA of 0 minus TA of 0. I'm just subtracting this from both sides. But a vector minus itself is the 0 vector. This is TA of 0 plus TA of 0 minus TA of 0. So this is TA of 0 plus 0, which is TA of 0. So we get TA of 0 equals 0. So the 0 vector in Rn is always in the kernel. Always. And another fact about the kernel is that the kernel is a subspace of Rn. That's a kind of a lemma or a theorem, whatever you choose to call it. Why is it a subspace? Well, subspace is a set of vectors closed under vector addition and scalar multiplication. So suppose x and x prime are in the kernel of T, and C is any scalar. So T sub A of x plus x prime, because this is a linear transformation, this is TA of x plus TA of x prime. But each of these is in the kernel. That's 0 plus 0, which is 0. So if x and x prime are in the kernel, x plus x prime is in the kernel. And if I take T sub A of CX, that's C T sub A of x That's c times the zero vector, and anything times the zero vector is zero. So this kernel satisfies the two properties that it's closed under vector addition and it's closed under scalar multiplication. So that's a subspace. Another subspace associated with a linear transformation, Rn, Rm, and here's this T sub A. You take any vector x that gets sent to T sub A of x over an Rm. And sitting here in Rm, we have all the vectors that come from vectors back in this space. And that set of vectors is called the image of this linear transformation. It's all the vectors y and Rm, such that y equals T sub A of x for some x in Rn. So you take everything in here and you look at their images, and it's not necessarily all of Rm is some subspace. That subspace is called the image. Well, actually, I'm calling it a subspace, but I need to prove that it is. So again, this is a kind of a lemma, if you like. The image of T sub A is a subspace of Rm. And the proof's as follows. Suppose I take two vectors y, y prime in the image of T sub A, which is contained in Rm, and I take any scalar. So if these are in the image of T sub A, there exist vectors x and x prime back in Rn such that T of A of x is equal to y, and T sub A of x prime is y prime. So y plus y prime is TA of x plus TA of x prime. But by the additivity of a linear transformation, this is TA of x plus x prime. That means this vector is the image of a vector back in Rn. So this is in the image of T sub A. So the image of T sub A is closed under vector addition, and C times Y is C times T sub A of x, but this is T sub A of C times x. This is a vector in x, so this is a vector in the image of T sub A. So this is a proof that the image is also a linear transformation. Let's look at an example, and then I'll look also at a couple of the homework problems. Suppose I let A be 1, 2, 3, 4. So this is a 2 by 2 matrix. So T sub A is a function from R2 to R2. And T sub A of x, it's the matrix times x1, x2. That's x1 plus 2x2, 3x1 plus 4x2. So this is, you take a vector, so this is my vector y1, y2 in R2. x1, x2 gets mapped to this. What's the kernel of T sub A of x? That's the set of all vectors x1, x2, such that T sub A of x is 0. That is, x1 plus 2x2 equals 0, 3x1 plus 4x2 equals 0. So we have to solve these two equations and two unknowns. x1 plus 2x2 equals 0, 3x1 plus 4x2 equals 0. If we solve these equations, we get that the only solution is x1, x2 equals 0, 0. So the only vector that gets mapped to 0 is the 0 vector. So the kernel of this linear transformation is just the 0 vector over in Rm. And what is the image? So the image of T sub A of x, then we write that it's all vectors y1, y2 in R2, such that TA of x1, x2, which is x1 plus 2x2, y 3x1 plus 4x2 equals y1, y2 for some x1, x2 in R2. So the question is, for what y1 and y2 can we solve this equation? If we have x1 plus 2x2 equal y1, and x3x1 plus 4x2 equal y2, for this system of equations, the determinant of the matrix 1, 2, 3, 4 is 4 minus 6 is minus 2 is not 0. So we know, in fact, that this set of equations always has a solution, right? We proved this already. If you have two equations and two unknowns, if the determinant of the coefficients of the x's is different from 0, for every y1, y2, there's a unique solution. So this image is, in fact, all of R2. So in this case, where we have R2 going to R2, the kernel is just the 0 vector, and the image is all of R2. Okay. Any questions about this? So let's look at some of the homework problems in this section. Exercise 1, we have two matrices to study. 1, 0, 0, 0 is the first. What is T sub A of x? That's 1, 0, 0, 0 applied to x1, x2. That's x1, 0. So this is equal to 0, 0, if and only if x1 is 0. So the kernel of T sub A, it's all vectors where the first coordinate is 0. So all vectors that form 0, x2. So if you look at the xy plane or the x1, x2 plane, these are the vectors where x1, the first coordinate, is 0. So the kernel is what we would call the y-axis. That's the kernel T sub A. And when you apply this matrix times a vector, you can get any vector where the second coordinate is 0. So the image of TA, it's all vectors x1, 0, where x1 is any number. That is the x-axis. That is the image of T sub A. And in fact, what this linear transformation does, it takes the vector x1, x2, and it just projects it onto the x-axis. This goes to x1, 0. So this is t sub a of x1, x2. So for this very simple matrix, the kernel is the vertical axis and the image is the horizontal axis. Any questions about that? The second part of this theorem is a different matrix. Look at the matrix 9, 3, 3, 1. So t sub a of x is 9, 3, 3, 1 applied to a vector x1, x2. That's 9x1 plus 3x2, 3x1 plus x2. So what is the kernel of this map? The kernel is all vectors x1, x2, where this is 0. So we have to find all solutions of these two equations. Now, the first equation is really just 3 times the second equation. So this is all x1, x2, where 3x1 plus x2 equals 0, or x2 equals minus 3x1. So that's the kernel. It's all vectors x1, x2, where x2 is minus 3x1, which is x1 times the vector 1 minus 3. So in the plane, this is all scalar multiples of 1 minus 3. That's 1 minus 3. And the set of all scalar multiples of it, it's just this line through the x-axis. This is the kernel of t sub a. These are all points that satisfy the equation. This is a line with slope minus 3. x2 is minus 3, x1. All the points that satisfy this equation. It's that red line. And what is the image? The image of t sub a, it's all vectors, x1, x2, where x2 is 3x1 plus x2, and x1, this is 3x2. Sorry, it's all vectors y1, y2, where y2 is 3x1 plus x2, and y1 is 3y2, or y2 equals a third y1. That's the line through the origin with slope a third. This is the point 1, 3. Slope a third goes. And y1 is 3, x2 is 1. It's this line. So this is the image of t sub a. So this matrix, the kernel is the line x2 is minus 3x1, and the image is the line y2 equals a third x1, third y. Right. Any questions about that?
How did you get the image again?
So I have the matrix A, which is 9, 3, 3, 1. Let me write my vectors as xy instead of x1, x2. So A applied to the vector xy is 9, 3, 3, 1 times xy. That's 9x plus 3y, 3x plus y. And I observe that 9x plus 3y is exactly 3 times 3x plus y. So let me keep it x1, x2. So it's x1, x2, x1, x2. So this is 9x1 plus 3x2, 3x1 plus x2, and 9x1 plus 3x2 happens to be exactly 3 times 3x1 plus y1, right? So this is my vector y1, y2, and I see that y1 is 9x1 plus 3x2, which is 3 times 3x1 plus x2, just by multiplying. And this is 3y2. So this is all vectors where y1 is 3y2, or y2, if you like, is a third y1. So this is y1, a third y1, or y1 times 1, a third. So this is the image. The image of T sub A, it's all vectors y1 times 1, a third. So in the plane, this is the vector 1, a third, 2, 2/3. It's this line through the origin. Right? So this is the line y2 equals a third y1. That's the image of T sub A. Does that make sense?
Yes, that makes sense. Thank you.
Okay. Problem 2 is a three-dimensional problem. We have the matrix A, which is 1, 0, 0, 0, 1, 0, 0, 0, 0. So T sub A is a function from R3 to R3. So what is T sub A of x1, x2, x3? It's 1, 0, 0, 0, 1, 0, 0, 0, 0, applied to x1, x2, x3. That's the vector x1, x2, 0. So if you want to think about what this means geometrically, if this is 3 space, you have your vector x1, x2, x3. If this is projected onto this horizontal plane, this is x1, x2, 0. That's what T sub A does. So T sub A projects every vector. I mean, if you want to look at this visually, geometrically, it projects every vector down into the xy plane, if this were xyz, or this x1, x2 plane. So what is the kernel of TA? It's all vectors that get sent to 0. It's all vectors x1, x2, x3. such that T sub A of x1, x2, x3, which is x1, x2, 0, is the 0 vector, which means exactly that the first two coordinates are 0. So it's all vectors, 0, 0, and x3 can be anything. And what is that? That's the z-axis. That's the kernel of T sub A. A vector projects onto 0 precisely when it's on the z-axis or the x3 axis. And what is the image of T? The image of T, it's all vectors, x1, x2, 0. That is, it's all vectors where the third coordinate is 0. That's this horizontal plane. So this xy plane, if you like, this is the image of T. So the image of T is this horizontal plane, and the kernel of T is this red vertical axis. Okay. And what about problem 3? So if we have a linear transformation, let's say from a vector space, suppose A is an n by n matrix. So it's a square matrix, not a rectangle. It's not really a rectangle, it's square. So this is a map from Rn to itself. And you might have a vector x where Ta of x is equal to x. So it's kind of like fixed. It doesn't move. If you apply Ta to the vector x, you get x, or which is nice. Or what's almost as nice is if you have a vector x and Ta of x doesn't twist or turn it in any way, it just stretches it. So Ta of x is lambda x for some lambda. So if this is x, it might stretch it or contract it or go in the opposite direction, but it's exactly on the same, it's on the line through the origin, on the line through the origin in x. So it doesn't twist or turn the vector, it just stretches it or flips it around 180 degrees and then it stretches it. So x in Rn is called an eigenvector. It's a German word that vector is vector. And eigen just means characteristic. It's an eigenvector with eigenvalue lambda if Ta of x is just lambda times x. So these are very important words in math, physics, all engineering, eigenvectors and eigenvalues. Because if you have an eigenvector for a linear transformation, you kind of understand what the linear transformation does to it. It just stretches it. It doesn't change its direction, really. So this exercise is really just an exercise to get used to the word. Suppose you have A is the matrix 9, 3, 3, 1. What is T sub A of the vector 3, 1? So you take 9, 3, 3, 1, apply it to the vector 3, 1. you get 27 plus 3 is 30. 9 plus 1 is 10. You get the vector 30, 10. And if you look at that, you see that's really 10 times the vector 3, 1. So T sub A of 3, 1 is 10, 3, 1. So 3, 1 is, for this function, 3, 1 is an eigenvector with eigenvalue lambda equal to 10. When you apply this linear transformation to this vector, it just stretches the vector by a factor of 10. That's all there is to it. All right. And in a few weeks, we're going to be spending a lot of time studying eigenvectors and eigenvalues. But it's just important to get to see what they are early on. Excuse me. All right. Okay. So that's the end of chapter 3. Sorry, of chapter 2. What comes next? Well, you might think after chapter 2 comes chapter 3 on determinants, which is a beautiful subject, but I'm going to skip it. And so next, we're jumping to chapter 4. All right. So that is, semester is short, and it would be lovely to spend a month on determinants, but it's more important in a beginning course in linear algebra to go learn more directly about general vector spaces and linear transformations. So that's where we are now. Okay. So this is chapter 4, which is vector spaces. We've been dealing with the vector spaces Rn and Rm and linear transformations. And we just looked at a linear transformation defined by a matrix. So I want to introduce vector spaces in general. We know particular examples are Rn, Rm, R2, R3, R4, and so forth. But in general, let F, well, the real numbers or the complex numbers or any field, but in fact, I think I'm just going to deal with R. So our field is always going to be just the field of real numbers. But everything you do for the real numbers, you could also do for the complex numbers. You could do it for the rational numbers. There are lots of fields you can deal with. So this is the definition of a vector space. A vector space is a set that's called V, whose elements are called vectors, with two operations: vector addition. So if you have vectors U and V, you can add them. There's some operation of vector addition, and there's an operation of scalar multiplication. Scalar multiplication. If you take a vector V and a scalar C, there's some operation of multiplying the vector by the scalar. So you have two operations, vector addition and scalar multiplication, and these have to satisfy certain properties. And if you check, all these properties will be satisfied by Rn, but Rn is just one example. Of a vector space. So what are properties of vector addition? It has to be associative. If you have three vectors, u, v, and w, you add u and v and then add w to that. That's the same as adding u to the sum of v and w. Has to be commutative. The order doesn't matter. U plus v equals v plus u. There has to be a zero vector where u plus 0 is equal to u for all u. And there has to be an additive inverse. So for all u, there always exists a v with u plus v equals 0. So addition satisfies these properties. And scalar multiplication has to also satisfy nice properties. 1 times any vector is the vector. There's a kind of associativity. You multiply two scalars, C1, C2, and multiply the vector by that. That's the same as taking the vector v, multiplying it by C2, and multiplying that by C1. And you have a distributive law, actually two distributive laws. If you take C1 plus C2 times any vector, that's C1v plus C2v. And if you take C times the sum of any two vectors, that's Cu plus Cv. So all of these properties are satisfied by Rn, but any set that has some operation of addition and scalar multiplication would also be a vector space. So what are some other examples of vector spaces? So examples of vector spaces. So the basic example is Rn for all n greater than or equal to 1. Another example, this is sort of the trivial vector space, is a set that just consists of the 0 vector, because 0 plus 0 is 0, and any scalar times 0 is defined to be 0. So just the set consisting of the 0 vector is a vector space. You could look at, let's call it, this is the notation I used in the book, Mn. MAT, this just means all m by n matrices. Because if you have two matrices, you can add them and you can scalar multiply them and everything is satisfied. We have the set R square brackets X. This is all polynomials in X. What's a polynomial? A polynomial is something that looks like, for example, P of X equal to 3x to the 5th minus 2x squared plus 7 is a polynomial. And if Q of X is 2x to the 9th minus x to the 5th plus 4x squared plus x, that's another polynomial. And if you add them, you just add polynomials. This is 2x to the 9th plus 4x to the 5th plus 2x squared plus x plus 7. And if you take a polynomial and you multiply it by something like 10 times p of x, you just multiply every coefficient by 10. So the set of polynomials is also a vector space. What's an example from calculus? Let's say C01. This is all continuous functions. F of x on the interval between 0 and 1. So this is calculus 0, 1. Take any function y equals f of x, continuous between 0 and 1. If you have two continuous functions and you add them, you get another continuous function. If you have a continuous function and you multiply it by a scalar, you have another continuous function. So there are lots of continuous functions in the universe. And, everything that we did in chapters 1 and 2 for Rn, almost everything carries over to these arbitrary, or if you like, abstract vector spaces. So this is the general definition of a vector space. It's a set in which you have two operations defined. There's an operation of what we call vector addition. You can add two elements of the set and get a third element of the set, and that operation satisfies these properties of associativity and commutativity and so forth, and scalar multiplication as well, that satisfies the properties. Yeah. Now, when we were looking at Rn and solutions of equations, we saw that if you take the set of solutions of a homogeneous system of equations, you always get a subspace. And we can define a subspace of a vector space, an abstract vector space. A subset W of a vector space V is called a subspace if, first of all, the zero vectors in W. Whenever W1 and W2 are in W, then the sum is in W. And whenever W is a vector in this subspace and C is a scalar, then C times W is in W. It's exactly how we defined the subspace of Rn. So a subset of a vector space is a subspace if it contains 0 and is closed under vector addition and closed under scalar multiplication. If W and W prime are in a subspace, then -1 times W prime, because this is just this vector multiplied by a scalar, is in the subspace, and W plus -1 times W prime is in the subspace, because this is closed under vector addition, and this is exactly what we call W minus W prime. So with this understanding of what subtraction means, every subspace is also closed under vector subtraction. So here we have a vector space V. Here we have a subspace W1. Here we have another subspace W2. And 0 is in both of these. And this is what's called the intersection. So let W1, W2 be subspaces of W. Sorry, subspaces of a vector space V. I claim that the intersection is also a subspace. And the proof goes as follows. First of all, these are subspaces, so W0, the 0 vector is W in W1, and the 0 vector is in W2, so the 0 is in the intersection. Because the intersection is everything, the intersection of two sets is everything that belongs to both of the sets. So if 0 is in W1 and 0 is in W2, then 0 is in the intersection. Second, if W and W prime are in the intersection, that means that W prime they're both in W1, and W prime, they're both in W2. But if W and W prime are in W1 and W1 is a subspace, W1 is closed under vector addition, so W plus W prime is in W1. And similarly, if both W and W prime are in W2, then W plus W prime are in W2. So they're in both of these. So W1 plus W1 plus W prime is in the intersection W1 intersect W2. So this set is closed under vector addition, and similarly is closed under scalar multiplication. So the intersection of two subspaces is another subspace. So it's actually very interesting in linear algebra to see what subspaces can be constructed from other subspaces. So suppose we take subspaces W1 and W2 of the vector space V. Suppose we define the sum of these two subspaces. So what does it mean to add two subspaces? Because these aren't elements, these aren't vectors, these are sets of vectors. So this is the set consisting of all vectors little w1 plus little w2, where w1 is in w1 and w2 is in the subspace w2. And I claim that this sum is a subspace also. So how do we prove that? First of all, 0 is in W1 because W1 is a subspace. And 0 is in W2 because W2 is a subspace. So 0 plus 0 is in W1 plus W2, but 0 plus 0 is 0. So the sum W1 plus W2 contains 0. So the first property of a subspace is satisfied. Suppose I let W and W prime be two vectors in W1 plus W2. So then W in W1 plus W2 implies W is equal to W1 plus W2 for some vectors W1 in W1, subspace W1, W2 in the subspace W2. And W prime is also in W1 plus W2. So W prime is equal to some W1 prime plus W2 prime for some vector W1 prime in W1 and W2 prime in W2. But if W1 and W1 prime are both in W1, then W1 plus W1 prime is in W1. And if W2 and W2 prime are in the subspace W2, W2 plus W2 prime is in W2 also. Which means if I add these two vectors, W1 plus W1 prime plus W2 plus W2 prime, that's in W1 plus W2. But just by using associativity and distributivity, and commutativity rather, this means that W1 plus W2 plus W1 prime plus W2 prime is in W1 plus W2. So this set, W1 plus W2, is closed under vector addition. And in the same way, we can show that it's closed under scalar multiplication. Okay, now, any questions? This is all interesting stuff. I want to look at section 4.2, which is on linear combinations. So when we were looking at vectors in Rn, if you had vectors v1, v2 up to v sub k, and you multiplied each of them by a scalar, and you added, this was what is called a linear combination of vectors. And exactly the same definition extends to abstract vector spaces. If you have a vector space V and vectors v1, v2 up to v sub k, vectors in V, and scalars c1, c2, c sub k in R, you can multiply each vector by a scalar, and then you can add, and that is what is called a linear combination of v1 up to v sub k. So this is what we are already long familiar with. And a very important result is the following. So this is theorem 4.4. Let S be a non-empty set of vectors. The set of all linear combinations of vectors in S is a subspace of V. And the proof goes as follows. Let's just consider the case when S is a finite set. So S consists of vectors W1, W2, up to W sub K. And we let W be the set of all linear combinations of these vectors. That's all vectors of the form C1W1 plus C2W2 dot 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 CKWK, where C1, C2, and so forth up to CK are real numbers, are scalars. So I want to show this is a subspace. Well, all you have to do is show that it's closed under vector addition. So suppose we let W be a vector that looks like this. And we let W prime be another linear combination. Say the scalars have primes on them, C1 prime, W1, CK prime, WK. But when you add, just by using the fact that everything is commutative and distributive, this is C1 plus C1 prime times W1 up to CK plus CK prime times W2. And this is in W. So this set of linear combinations is closed under scalar multiplication. I mean, let me just give an example to show what this means. Suppose K is 3. Suppose I had 2W1 minus 5W2 plus 9W3. And I had 8W1 plus 11W2 minus 20W3. When I add them, I have 2W1 plus 8W1. That's going to give me 10W1. Minus 5W2 plus 11W2. 11 minus 5 is 6. 9W3 minus 20W3 is minus 13W3. So this linear combination plus this linear combination is this linear combination. And if I took the 2W1 minus 5W2 plus 9W3, and multiply it by a scalar like 7, when you just distribute across, this is 7 times 2, 7 times 5, 7 times 9. Again, we have another linear combination. So the set of all linear combinations is closed under addition and scalar multiplication. So given any set of numbers, any set of vectors, you can get a new subspace by taking their linear combinations. And we have a name for this. We call this the subspace of V generated. This is the word, generated by S. It's the set of all linear combinations of the vectors in S.
Question, wouldn't it be 10W1 plus 6W2 minus 11W3?
Let's see. 10 plus 6, 9 minus 20 is 11. Yes, thank you. Yep, that's what it is. Okay, good. And this subspace generated by S, sometimes denoted by S in these brackets. I want to make sure that I introduce a lot of the fundamental definitions today. So the next is linear dependence and linear independence. So we say set S of vectors is called linearly dependent if there are distinct vectors V1 up to V sub k in S and scalars C1 up to C sub k such that the linear combination C1 V1 plus C2 V2 and so forth up to CK VK is the zero vector, and not all the scalars are zero. C sub I is different from 0 for at least one I, for some I. So V1, V2, V sub k, these are pairwise distinct vectors. There's some linear combination that gives you 0. If every scalar C1 were 0, you would just be adding the 0 vector to itself k times, and that's 0. But if there's some linear combination with at least one coordinate, at least one scalar C1 non-zero, then the set of vectors is linearly dependent. And these have to be distinct. It would be cheating to say that 3 times V1 plus minus 3 times V1 is 0. That's true, but these are the same vector, so you have to be taking different vectors in your set. And a set S of vectors is linearly independent if it's not linearly dependent. So that's clear enough. So here's a little exercise. Spend a minute to do it. Are the vectors 6 minus 14? Well, that's V1. and V2 equal to minus 1535 linearly dependent or independent. So think about that for a second. I'll pause the recording. Let's see, is there an answer? Are these linearly independent or linearly dependent? If I have 6 times minus 14, I might notice that this is 2 times the vector 3 minus 7, and minus 1535 is minus 5 times the vector 3 minus 7. So if I were to take minus 5, no, if I were to take 5 plus 5 times the vector 6 minus 14, plus 2 times the vector minus 1535. This is the vector 30 minus 70, and this is the vector minus 30 plus 70. And when I add, I get 30 minus 30 minus 70 plus 70, which is 0, 0. So here I have a linear combination of my two vectors with scalars that are not both 0. In fact, they're both non-zero. So because I have a linear combination of these vectors with non-zero scalars equal to 0, these vectors are linearly dependent. That's what we can say.
Can you repeat what you did on that last step with the 5 multiplying by that specific vector and 2 multiplying the other vector?
Well, 5 times this, you multiply a vector by a scalar, you multiply each coordinate by the scalar. So 5 times 6 is 30, and 5 times minus 14 is minus 70. Right? And here I'm multiplying this vector by 2. So the first coordinate is 2 times minus 15 is minus 30. And the second coordinate is 2 times 35, which is plus 70. And then when I add these two vectors, I get the 0 vector. So here I have the linear combination of these two vectors with scalars not both 0. That gives the 0 vector. So that's the definition of linear dependence. That means these two vectors that I started with are linearly dependent. And you might say, well, how did I get the 5 and the 2? Well, I was sort of lucky because I noticed this vector, 6 minus 14, is 2 times 3 minus 7. And the second vector is minus 5 times 3 minus 7. So that suggested a way to find the coefficients. But if I didn't see that, I could still do the problem, and I would do the problem like this. We have the two vectors, let's see, 6 minus 14 and minus 1535. And the question is, what linear combinations of these vectors give 0, right? Can I find x and y so that this equation, this vector equation, gives the 0 vector? Of course, x equals 0 and y equals 0 will do that. The question is really whether there's another solution. But of course, this is the same as the vector 6x minus 15y and minus 14x plus 35y. So this vector equation is equivalent to this, which means we're looking for scalars x and y, where 6x minus 15y equals 0, and minus 14x plus 35y equals 0. So I want to solve these two equations and two unknowns. So I can solve two equations and two unknowns, any way that I learned in high school or in linear algebra. It doesn't matter. For example, if I multiply the first equation by 7, I would get 42x minus 105y equals 0. And if I multiply this equation by 3, I get minus 42x plus 105y equals 0. Actually, they're sort of like the same equation. So let's see. What's something better that I can do? Well, the first equation says 15y equals 6x, or y is 6 over 15x, or 2/5 x. And if I plug that into the second equation, minus 14x plus 35y, that's 2/5 x, I get minus 14x plus 14x equals 0. So any vector with y equal to 2/5 x, or any pair of numbers, will be a solution of this equation. So if I want to avoid fractions, if I let x equal 5 and y equal 2, I get a non-trivial linear combination. In fact, I think that's exactly the linear combination I had before. So I have a non-trivial, non-zero linear combination of these two vectors that produces the 0 vector. So by definition, these two vectors are linearly dependent. Let's look at a very nice example. So in R3, supposed to let E1 be 1, 0, 0, E2 be 0, 1, 0, and E3 be 0, 0, 1. Suppose I take some linear combination of these vectors. x1, E1 plus x2, E2 plus x3, E3. So x1 times E1 is x1, 0, 0. x2 times E2 is 0, x2, 0. x3 times E3 is 0, 0, x3. When I add, I get x1, x2, x3. And I want to know, when is this linear combination equal to 0? Well, it equals 0 if and only if x1 equals x2 equals x3. So therefore, the set of three vectors, x1, x2, E1, E2, and E3, are linearly independent. These are linearly independent vectors. There's an analogous statement for any Rn. There's a very useful symbol in mathematics called the Kronecker delta. Kronecker was a German mathematician in the 19th century. It's delta ij. And this is defined to be 1 whenever I equals j, and 0 if I is different from j. So delta 2 is 1 because these are the same. Delta 3 is 0 because 3 and 7 are different, right? In fact, if you look at the matrix, the n by n matrix, let's make it 3 by 3. The 3 by 3 matrix, where the coordinates are delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. Whenever the subscripts are the same, 1, 1, 2, 2, or 3, 3, the value of this Kronecker delta is 1. When the subscripts are different, which is every other pair, the value is 0. So this is the identity matrix. So you could think of the Kronecker delta, delta ij, being the coordinates of the Kronecker matrix, but it's a very, very useful function in mathematics. And in Rn, if you take the vector E1 to be 1 and everything else 0, and E2 to be 0, 1 and everything else 0, and so forth down to En, which is the last one where everything is 0 except the last coordinates. The vector E sub j, this is the vector with the zeros everywhere, but a 1 in the jth coordinate. And you could write this, if you like, as delta 1j, delta 2j, delta jj down to delta nj, because this is the jth coordinate would be 1 and everything else would be 0. So these are important ideas to become familiar with. Linear dependence, linear independence. And again, many of the results that were already proved about vectors in Rn hold exactly for linearly independent vectors in an abstract vector space. So this is an example. This is theorem 4.6. So that V1, V2 up to V sub k be a set of linearly independent vectors. That x1, x2 up to x sub k and y1, y2 up to y sub k be scalars, such that if I take the linear combination of the vectors v with the scalars x1 up to xk, so x1 v1 plus x2 v2, up to xk vk. And I take the similar linear combination of these linearly independent vectors with the y scalars, y1 v1 plus y2 v2 to yk vk. This vector and this vector are equal only in the trivial case, if and only if the scalars are exactly the same. x1 equals y1, x2 equals y2, x3 equals y3, up to xk equal yk. So if you have linearly independent vectors, every vector in the subspace they generate has a unique representation as a linear combination of those generating vectors. And the proof will go as follows. So let me use summation, sigma notation. So summation xi vi, I goes from 1 up to k. That's what this is. And this is summation yi vi. I goes from 1 up to k. These are equal if and only if their difference, if you subtract summation xi vi, I goes from 1 to k, minus summation yi vi, I goes from 1 to k, is 0. But this is exactly the same as summation I goes from 1 to k, xi minus yi times vi. And this is a linear combination of v1 up to vk with these scalars. But the vectors v1 up to vk, we were told, are linearly independent. So this is a linear combination of v1 up to vk, and this happens if and only if all the scalars are 0, xi minus yi equals 0 for all I, which is the same as saying xi equals yi for all I, which is exactly what we wanted to prove. Okay. All right, so this is what we might call real linear algebra. Real not in the sense of the real numbers versus the complex numbers, but real in the sense that we're no longer dealing with the very special, even though it's a very important case, of the vector space Rn of column vectors, but arbitrary vector spaces. All we know about the vector space is that there are operations of vector addition and scalar multiplication, and these operations satisfy the nice properties that we would like to see. Associativity, commutativity, distributivity, and so forth. Okay. All right. So now we're up to we're doing chapter 4, and we're going to be doing chapter 4. The goal is chapter 4 and chapter 5. That's the first half of the course is chapters 1 and chapters 2, and the second half is chapters 4 and 5. So that's what we're doing now. And we will see that a lot of what we're doing in chapter 4, we really already saw in chapters 1 and 2. That is, once we understand the special cases of Rn, for any n, we have almost everything there is to say about vector spaces of any vector space. Okay, that is it for today. Any questions before we stop? Again, I remind you that Monday, Tuesday, Wednesday, Thursday, 7 p.m. I have a Zoom session if you have questions, and I encourage you to log on and ask questions. And if you have questions and you can't make that 7 o'clock time, just send me an email, and we can always work out a time where we can meet privately on Zoom. And I'm happy to answer all your questions then. Okay, that's it then all. Thank you. See you Wednesday.